Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Uh, Now we're going to continue our lecture on fatigue and fracture mechanics. Lecture 10. We're going to talk about the fracture mechanics design. The outline of today's lecture is the first one is the design approaches, and then the fracture mechanics design, and then we do some design example. Right. For the first approach, it is about the traditional approach, where the traditional approach is actually the synthesis of various disciplines through statics, strength of material, structural analysis, matrix algebra, and etc. To create a structure that is proportioned and then detail into its final shape. The design involves the process of detailing and proportioning members to carry the given loads without exceeding the allowable stress. The allowable stress is usually a certain percentage of the yield strength for tension members and a certain percentage of the buckling stress for compression members. Alright, the traditional approach always use the yield strength as the benchmark. Okay, there is some kind of assumption when we use the traditional approach. The first one is assume the perfect fabrication, in that the structure are usually assumed to have no crack, like discontinuities, defects, or crack. Means that the perfect fabrication is the structure has no flaws. I mean, it is like a perfect geometry. There is no other thing that make it look a little bit defects. So it is also assumed that structural materials have sufficient ductility to yield locally and redistribute the loads in the vicinity of the stress concentrations or mild discontinuities that may be present. Alright, there's another approach. This is the traditional approach, while this one is the fracture mechanics approach. First of all, this fracture mechanics approach, it follows the traditional approach, but also involve the selection of a material and of the appropriate design stress level at the particular surface temperature and loading rate to which the structure will be subjected. The selection of materials and allowable stress levels is based on the realization that discontinuities in large complex structures may be present or may initiate under cyclic loads or stress corrosion cracking, and that some level of notch toughness, which is a different property than ductility, may be desirable. We involve some kind of iteration for us to predict what is the geometry that we need to apply within the structure uh, using this fracture mechanics approach. Fracture mechanics design, the fundamental design approach to preventing fracture in structural materials, is to keep the calculated stress intensity factor K1, the driving force, below the critical stress intensity factor K1C, which is, we consider that as the resistance force. This is analogous to keeping sigma to be less than the sigma yield to prevent yielding. Okay, still inside the perspective of fracture mechanics design, a general design procedure to prevent fracture in structural members is as follows. The first step, you have to calculate the maximum nominal stress, sigma, for the member being analyzed. Second, estimate the most likely flaw geometry and initial crack size A0 to design against fracture during the expected lifetime of a structure. Estimate the maximum probable crack size during the expected lifetime. Three, calculate K1 for the stress sigma n flow size A using the appropriate K1 relation. Fourth, determine or estimate the critical stress intensity factor K1C by testing the material from which the member is to be built. These critical stress intensity values are a function of the appropriate service temperature and loading rate. Okay, what they mention here is that what they means here means is they already give you some kind of value at appropriate service temperature that we want to operate the design. So we need to use that value so that it will not uh, so that it will be suitable for the design temperature. Okay, alternatively, appropriate critical stress intensity values can be estimated from CVN impact test results. Compare. The last one is to compare K1s and K1C. From here, we need to design against fracture, ensure that K1 will be less than the critical stress intensity factor K1C throughout the entire life of the structure. This may require the selection of a different material or reduction of the maximum nominal service stress. Also, it may require better quality control during fabrication or periodic inspection for cracks throughout the life of the structure. Okay, we will see an example that will be shown here following each step of the fracture mechanics design. Okay, this is a plot of the nominal stress. Once you increase the stress, you will check how much the increasing flow size will affect this stress. So, for example, if I take the K1C or Kc critical value for one type of material, let's say this is the plot. So, for example, we have initial crack a node here. Of course, we're going to have sigma node. But then, at several type, at certain level of flow size, for example here, I can get what is the sigma f, final sigma. Right. If we want to have a larger or a higher level of stress while we maintain the same increasing flow size, we need to implement tougher steel. For example, in this case here, so the plot will be increased. So we just can extend the level of increasing stress here. Okay, let's see this figure. This is one type of geometry. If I have a middle crack here, and then the crack length is 2A, and then I have load acting on both sides as a tensile load. Okay, we know that Kc for this case is sigma times uh, this parameter, but then we can rearrange that to find uh, the sigma c or the critical stress using this critical stress intensity factor. So this is the plot of sigma versus A. To prevent yielding, sigma must be below than sigma y. To prevent fracture, the actual stress sigma and flow size A must be below the K1C level. So we need to check for both conditions. The first one is to prevent yielding, and then the second condition is to prevent fracture. Okay, next, let's assume that the engineer has established the following general information The first one is the type and overall dimensions of the structure, for example, bridge, treasure vessels, landing gear, wing, and so on. Second, the general size of the tension members, which is the length diameter has been verified. We already know what is the general size of the tension members. Okay, the third, additional performance criteria and service conditions, for example, minimum weight, less cost, maximum resistance to fracture, specified design life, loading rate, operating temperature. Most likely, will be given in the example. Okay, the last one, you need to apply stress and cyclic stress range where crack growth can occur. Okay, as will be discussed later. Okay, there's two type of condition or we say that as principles. The first one, okay, the first one is the fail safe and safe life. But what is this for? Okay, the objective is to keep the applied K1 below the critical K1C. This one we need to observe because we want to prevent a fracture. So throughout the life of the structure, there are two principles. The first one, fail-safe, in which assumes that if an individual member fails, the overall structure is still safe from total fracture. Right? If an individual member fails, mean if let's say one single structure fail, but the structure can still we use that for the operation. Okay, and then apply for structures with multiple load paths because of structural redundancies. Okay, for another principle, it is the safe life. Assume that for the particular service loading, the structure will last the entire design life of the structure and failure will not occur while the structure is in service. Means that if let's say a failure occur on that structure, means that the structure cannot be used anymore. Okay, it may or not have structural redundancies. Okay, the safety of a structure against failure by brittle fracture can be analyzed in the following manners. First, determine the values of the appropriate critical K value, K1C, K1D, etc., and the corresponding yield strength at the service temperature and loading rate for the materials being considered for use in the structure. Second, select the most probable type of flaw that can exist in the member being analyzed and the corresponding K1 equation. Complex shape flaws can be approximated by one of the models discussed earlier. Okay, the third one, determine the stress flow size relation at various possible design stress levels using the appropriate K1 expression and the appropriate critical K1C value. Okay, this one we have covered last time. Like for example, if I have a crack through, or we say this as a true thickness crack. So this is how we calculate for the K1, or we say that is stress intensity factor. The same if I have a surface crack, we need to implement this value where we need to find what is the Q value for this equation. Okay. And then for the edge crack, we need to use this equation 1.2, 1.12. Right, this is the examples of sigma versus A that we just briefly introduced just now. But this is with several type of value. a range of value. So, for example, if I take K1 equal to sigma times square root of pi A, for example, this is the case through thickness crack. So, we have this type of plot. So, assume that the material being analyzed has a K1C equal to 50 KSI times square root of inch at the surface temperature. Okay, they didn't specify the surface temperature, but they already give you the numbers. So, it doesn't matter. And sigma Y equal to 100 KSI. So we need to substitute the K1 equal to K1C. Okay, like this one, they substitute 50 into this equation, and then we need to find what is the value. Okay, for example, we have two plots here, the nominal stress versus flow size. And then this is the plot for K1C equal to 50 KSI. And then this is for K1C equal to 100 KSI times square root of inch. So you can see, even if I have a flow size, let's say 1.5 K1C for this graph, the nominal stress will be 20 KSI. For example, this is just for example. Let's say for the same flow size, but we have a different value of K1C, it will be higher, which is will be 40 something. Okay, this is the example, design example. Now we went to into we're going to check for the example how we're going to apply the fundamental that we have covered just now into the equation. Okay, selection of a high strength steel for a pressure vessel. All right, the question: we want to build a high strength steel pressure vessel to withstand 5,000 psi of internal pressure P. So the internal pressure is indicated by P symbol, that the diameter D of the vessel is nominally 30 inches, and that the wall thickness T must be equal to or greater than 0.5 inches. Okay, this is the constraint given by the users, where T must be equal to or greater than 0.5 inches. So when they give you this type of constraint, let's say once you calculate, you get the wall thickness as 0.3 inches, means that you cannot take the material that give you T equal to 0.3 inches as the selection, as the material selected. You need to take greater than that or equal to 0.5. Okay, the designer can use any yield strength still available, but in addition to satisfactory performance, for example, the material that we use must be lightweight, or it is anti-corrosion, or it can stand under several type of condition or environmental factors. So this is under the satisfactory performance, and then you also need to consider the cost of manufacturing. For example, the cost of the material, and then the weight of the vessels are important factors that must be considered. Right, the steel available for use in the vessel are shown in the table along with the yield strengths, assume K1C values at the surface temperature, and assume cost of each steel. For example, in this table 6.2, they already give you several type of steel, A, B, C, D, E, F, and each steel they have different type of yield strength and different type of critical stress intensity values. Also, they already estimate what is the cost of that material in USD per pound. So they measure that based on the value of the weight. Alright, let's say we go for the first case, which is we need to use the traditional design approach. The traditional design approach is to assume perfect fabrication, and therefore there is no flaw. Right? This is the condition that we have covered just now. We need to assume the structure as perfect, without any crack, without any discontinuities. So the factor of safety would be based on the yielding only, the yield stress. So yield stress is the most important factor here. Okay, based on the figure, or we say this based on this table, each of the steel they already give you what is the value for the sigma yield. Okay, it is also mentioned the user requirement for a factor of safety of 2. Okay, factor of safety. The user already give you. We need to make sure that the design can stand 2 times of the design of the prediction. If, for example, if I say a material or structure can stand, when we calculate, it can stand 100 kilonewton load. So if we say that the safety of factor of safety for that geometry, you should increase that 2 times from the one that you calculate. Means it can stand up to 200 kilonewton. Just now is 100, now it's become 200. So using that equation, which is sigma design equal to sigma yield divided by 2, means that the sigma yield is actually 2 times of the design. If you bring 2 times with sigma design, you can get what is the value for sigma yield here. This is just for the design. While they already give you the value for each material. This is for the design. Okay, so also you need to apply, because we want to calculate for the geometry. So the geometry is actually the thickness equal to P is the load, D is the diameter. Here, P is the internal pressure, D is the diameter of the vessel, 2 and sigma design. Sigma design will be taken from here. So it will be very simple, very straightforward, where you just need to substitute all the values here. And then let's say they just give you this, and then you need to add another column. For example, in this case, 260 divided by 2, you will get that as 130. Okay, using this value 130, this is sigma design. You insert this value into this equation, and then P will be equal to this value, which is 5000 psi, while D is 30 inch. So you will get the T equal to 0.58 inch. Okay, they already give you that the condition must be equal to or greater than 0.5 inch. In this value, in this table, let's say you take that as 0.58, so it can be considered. Okay, the weight now is 185. So the cost will be $259. Alright, and then we just need to repeat for other steel, and then find what is the value. Okay, this is actually this is the end of the traditional design approach. So you just stop up to here. You know what is the weight, the thickness, what is the weight, and then what is the cost. Okay, from there we need to do another analysis, which is the case 2, fracture mechanics design. In this case, it is assumed that the flaw is present. Means that if we want to compare with the case 1 is assume perfect fabrication, means there is no flaw. But here we need to assume a flaw is present, means there is a crack. We assume that. Okay, let's see. In this example, for example, we have the crack as 2C. So the maximum possible flaw size is estimated on the fabrication, inspection, and service consideration. Okay, let's see. Let's say we expect that the crack is the surface crack in this case, like this one, surface crack here. Okay, I have the thickness is A, while the length is 2C. Sorry, A is the crack length, while the thickness of the crack is 2C. So we assume that A equal to 0.5 inch, where you will get A divided by 2C equal to 0.25. So this is one of your parameter. Okay, from there, stress intensity factor equation for this crack model is given by K equal to 1.12 sigma times pi times A divided by Q times MK. This is not like this. This is just a surface crack, but we are talking about the pressure vessel. So we need to introduce another condition with another parameter, which is MK. Okay, MK and Q are defined and evaluated as discussed earlier. You may check the one that in the previous lecture. So like this one, I have 2C and then A is the correct line here. So if we take a look at the cross-sectional area, D is measured from the inner diameter, while pressure inside the vessel is P, and then the thickness is here, T. What is the thickness of the cylinder? So if we rearrange this equation, we can get this equation in terms of stress. You just need to bring everything here to this side, and then what is sigma. So let's say I have this type of this sigma. Okay, if we take the factor of safety of 2 against fracture, okay, like the same approach that we apply here for a factor of safety 2 that we just apply in the traditional design approach. Now we use the same factor of safety 2 against fracture. So here, based on this equation, we know that K1 design is actually K1C divided by 2. So we just need to substitute this equation into this equation. So we'll get, this is the final equation for the sigma design. Okay, just take this one, put it here, and then you will get this formula. Okay, from sigma design, T can be calculated from pressure vessel equation, which is T now equal to PD divided by 2 sigma design. Just the same like what we did in the traditional approach. Okay, recall different value of K1C for steel we are considering, where this is the same table as 6.2. We have several type of steel and then different type of value of yield strength and different value for K1C. Also the cost. Okay, for A equal to 0.5 inch, we can calculate sigma design and then T for each of the steel in the table. But because MK is the function of T and Q is the function of design stress, an iterative procedure must be used. For example, for steel D, where sigma y equal to 100 ksi, let's see, we take this value. We actually need to apply for all of the steel, but let's say we take this value first, just for one example. So K1C will be 220. KSI times square root of inch. Okay, means that we want to analyze for scale D now. Okay, this is the iterative procedure. First, to get the initial estimation of Q and MK, where we need to assume sigma divided by sigma y equal to 0.55. Okay, let's say they already give you what is the sigma that we want to apply to the structure, so we can get this value. So from here, we need to check what is the value for Q, which is we obtain that as 1.4. You may check this more on chapter 6 in the book Barsom. So mk equal to 1. Using this value, we can get we can substitute all the one that we just discussed just now. Sigma y equal to 180 and k1c. And then from that, we need to apply the value into this equation that we just derived. Okay, from here we can get the sigma design, which is 95 KSI. Okay, for our pressure vessel P, which is given as 5000 PSI, we need to convert that as KSI for the consistency in terms of unit. So P is actually 5 KSI and D equal to 30 inch. Therefore, we substitute the value that we get from the sigma design to here, P as 5 and D as 30. We get the first iteration, T equal to 0.8 inches. Alright, for the second iteration where we obtain T equal to 0.5, we know that A is actually 0.5 because they already give you as a user's input here. A we say that the wall thickness T must be equal or to greater than 0.5 inch, means that the crack must be if I have a crack must be more than that. Okay, so we take the value as 0.5. It's not logic if you say that the crack is 0.3 or something, because we need to make sure that the wall thickness equal to or more than 0.5. So we take the crack length, for example, in this case is as 0.5. Okay, so we take A equal to 0.5 divided by T, which is 0.8 that we just obtained from the previous iteration for the first one. We obtain the ratio A divided by T equal to 0.63. So we need to find what is the value of mk. Before this, we just assume that S to be 1. But now we have this equation where 1 plus 1.2 times A divided by T, which is this ratio, 0.63. We need to substitute here, minus 0.5, and then we get mk equal to 1.15. Right, now we check for the this ratio, sigma design divided by sigma y, where we get this value from the previous iteration here, 95 KSI. So 95 divided by 180, we get this as 0.53. The same, we need to check for the curve, what is the value of Q. So from here, we obtain Q equal to 1.4. Now, once we get the new value, we need to put this all of these values into the same equation. Right, now we have 110 times this Q, 1.4, and then A is 0.5. Now MK is no more 1, it's become 1.15. So we obtain a new sigma design, which is 82.2 KSI. Get using this value, we substitute into the same equation as this one. Now we have T. The target here is to find what is the new T. So T is the thickness. We obtain that as 0.91 inches. So we compare this value 0.91 and this the other one, which is 0.8 inches. Now we need to do another iteration to check either the consistency is okay or not. Alright, for the third iteration, we take the t value as 0.91 inches, and then we check for the ratio of a divided by t equal to 0.5 divided by 0.91. We obtain that as 0.55. We take this value and then insert this value into MK equation, and we found that MK equal to 1.06. So from there, we need to find what is the ratio between sigma design and sigma yield that we obtained from the previous one, which is 82.2 divided by 180. Now we obtain that as 0.46. So check from the figure, from the curve Q, we obtain that as 1.42. So as the same procedure that we applied just now, we just need to repeat the same but different using different value, which is in this case is 110 times 1.42 Q, and then the value of A, and then this is the value for MK. Now we obtain the sigma design equal to 90 KSI. Okay, using this value 90 KSI, we check for thickness, where we obtain the thickness as 0.83 inches. Okay, if you see, there is no some kind of consistency, where for the third iteration you obtain the thickness as 0.83, the second iteration 0.91, and then the first iteration is 0.8 inches. So we need to take the value in between of that, 0.8 and then 0.91 and then 0.83. So that's why they say that assume that t will be 0.85, so that it will be in between of that value. Okay, let's take a look at here, where we take t equal to 0.885. So we obtain AT equal to this value 0.95. Check for MK, which is now MK is 1.11. So sigma design, we take this value as well, 90, for from the third iteration. It doesn't matter because it's just like almost the same. 90 divided by 180, we get that as 0.5, and then from the curve Q equal to 1.42. Okay, 1.42, we check for the sigma design, we obtain that as 85.8 KSI. This is for the thickness, and then we check for the thickness, we get that as 0.87. If you see the trend, the first one we obtain 0.8 now, and then for the second iteration 0.91, and then for the third iteration 0.83, and then we assume that in between of that 0.85, while we obtain that the last iteration here as 0.87. Okay, now we almost the same. We already get the trend. It's not beyond that, or it's not less than that. We take the fifth iteration as is it, which is t equal to 0.87. Check for AT, and then check for MK as well. The design, sigma design, we obtain from fourth iteration, which is 85.8, almost is 89. 86, almost 86, so we just put 86. Divided by 180, we obtain that as 0.48, and then from the curve Q equal to 1.46, 42, 1.42, and then we check for the sigma design here, we get that as 87 KSI, and then we check for T, which is we obtain here 0.86. If you check, if you compare that with the fourth iteration just now, we just obtained that as 0.87. Now we obtain that as 0.86. It's almost the same. The value is almost the same. So we can stop here since nu t is very close to t from the previous iteration. Alright, once we obtain all of the, for D for example, we obtain that the sigma design as 87, and then the thickness is 0.86, and then we need to repeat the same procedure for other steel as well, like for example steel A, steel B, C, D, and F. D we just done it, E and F, sorry. So once we get all the values, we can check what is the weight for each material and what is the cost of manufacturing that pressure cell. Now we need to do a comparison between the traditional approach and the fracture mechanics approach, which is the traditional is in case 1. Here the thickness is based on the yielding. So the thickness required for factor of safety 2 against yielding, as in this column, and then the case 2, which is this is based on the fracture mechanics approach, we obtain as this value. Now you need to compare for each steel which is the highest thickness, so that we can prevent, at the same time we can prevent the yielding and the fracture. If you just take this value 0.85, you still cannot prevent the fracture. Now once we get the maximum value of, for example in this case for steel A 2.14, here we can prevent both condition. For example, what we can prevent the welding and also the fracture. Okay, if we go forward, we found that for example steel E, I have the thickness required for yielding against the yielding is 1.07, while for fracture is just 0.79. The trend is means that the yielding is the critical factor compared to the fracture. So we need to take the most critical value, which is 1.07. The same like in steel F. Okay, from that we can check using this value. This is the final value because we already consider two type of condition, the yielding and fracture. Now we need to check what is the weight and the cost for the manufacturing for each type of steel, A, B, C, D, E, F. So this is the cost and this is the weight that we have obtained from the thickness. Okay, this is the decision based on the analysis. Based on this table, we make the analysis and we can do the selection. From here, steel D would be the optimum selection on the basis of minimum weight, and steel F would be the less expensive steel. So as an engineer, you need to select based on the user's requirement. Either they want to have a lower cost of manufacturing, or they want to have a lower or minimum weight based on the requirement. But you can give them several options. Like in this case, you have 6 type of steel. Now it's time for them to decide which steel that they want to be implemented for the fabrication of the preserver cell. Note that for both cases, the factor of safety against both yielding and fracture are 2.0 or greater. Thus, the vessels are compared on an equivalent performance basis and show the advantage of using fracture mechanics during the material selection process. Okay, that's the end of this lecture. Next topic, we're going to talk about the elastic plastic fracture mechanics. So thank you very much. If you have any other question, you may raise that in the discussion, online discussion. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh.